Okay, so now I just want to just quickly recap what we're doing so far. So then the idea was that we start off with the idea that how to understand sums of random variables. So we did the example of two Poisson guys, the independents. So on the left hand side, we immediately see that that this that if they're independent, the sum is given by the convolution. The distribution of the sum is given by the convolution. And once we have that, then we're able to work out that an interesting fact that that if z Poisson adds up. So if x was Poisson lambda 1, y was Poisson lambda 2, they were independent, then z was Poisson lambda 1. Then you can generalize this. This proof is by induction. If you have k random variables, they're all independent, then the sums of them will also, and they're Poisson lambda I, then the z gives you a Poisson of the sum. Then you come here, then we notice that if x is Poisson lambda 1, y is Poisson lambda 2, and I ask you the distribution of x given z equal to n. We did this calculation using the definition of conditional probability, and we found out, lo and behold, if the chance that x is equal to k given z equal to n was n choose k lambda 1 by lambda plus 2 whole power k times 1 minus the same fraction to the power n minus k. And this we figured out was the same as saying that x given z equal to n was binomial n of lambda. It's an interesting fact. If you have two Poisson, you conditional sum, then the individual Poisson becomes a binomial. It's an interesting fact. And this understanding distribution of functions relied on the following theorem, which we've been using computationally in all the examples, is that if you have a function of n random variables, then all you're using the fact is that the function of x1, xn lands in the event b is the same as x1, x2, xn landing in the event f inverse b. And once you capture this idea, then everything else follows by simple plan. Let's move on to the next topic.
Yeah, Shiva, can I just ask a small question? Shiva?
What I want to do was I want to remove split view. Split view is good. It's yes, section. So I want to understand this idea of functions and independence. So 3.3.2 is functions and independence. Sure.
Yeah, can you hear me?
Can you ask it on chat? Is it possible? I'm sorry. Okay, let me carry on. I'll come back and answer the question when it comes. So now, so there was a question on the previous slide. Let me just go back again. Let me repeat the answer. So the idea was that, so we had shown in this computation that if x was Poisson lambda 1, y was Poisson lambda 2, and z was x plus y, then the distribution of x given z equal to n was given by a binomial n comma. So what I meant to say in terms of intuition was the following, that that this is a computation we have done. So x given z equal to. So, and we understood Poisson in this class so far as the limiting distribution of binomials. But the idea is that there's an interpretation of Poisson that you can use in a queuing model, where this interpretation of x given z equal to n being binomial is very useful. That's all I meant to say. So it's a little bit outside the scope of this class, but we will come and sort of, I'll try and see if I can motivate it at some point. Now let me go on to functions and independence. So now here the idea is the following. If x and y are independent random variables, right? And then I have functions f, let's say x takes values from s to t1, y takes values from s to t2. Then I have a function g from t1 to r. I have a function f from t2 to r. And I look at z equal to f of x, so g of x. I look at w equal to f of y. So there's no reason to believe, so if x and y are independent, there's no reason to believe that z and w will not be independent. So this should actually imply that, let me write this a little bit better so it's clear. So, let me go back to black. So g of x and w is equal to f of y. There's no reason to believe that z and y are not independent. So this will actually imply z and w are also independent. Because w depends on y alone, z depends on x alone. If x and w are independent, x and y are independent, then z and w should be independent. This is something that's sort of classical. Intuitively, it kind of makes sense. So this intuitively it makes sense. Right? Intuitively it makes sense. So let me try and write a theorem down that will sort of classify this properly. So let n be greater than or equal to 1, be a positive integer. So be a positive integer. So I'll take bigger than 1, so that way I at least have 2 random variables in my collection. So I'll write a general theorem down. And let's say I take j in the event 1 up to n, in the set 1 up to n. And I define for j in this set 1 up to n, I define a positive integer m sub a. M sub j. And suppose I have xij. So xij is what? J is in 1 to m. So j goes from 1 to m. J is in 1 up to n. And I is from 1 up to m sub j. So be an array of mutually independent random variables. For j in 1 up to n. So this already I already said this, no need to say this. Then I let f sub j be functions such that f sub yj is f sub j of x1j up to x, let's say xmj j are well defined. So that means f sub j's are well defined on this collection of random variables x1j to xmj. So each fj acts on different spaces, r sub mj perhaps to realign. Then, so they're all independent. So this is crucial. They're all independent variables. This collection. Then if I look at y sub j are also independent, then the resulting random variables y1, y2, yn are mutually independent. So the general fact about random variables that one can sort of use in the sense that, so general theorem one can write down. So in terms of function random variable. So if you have a random variable, an array, then and the array is defined in such a way that you have separate functions acting on independent parts of the array, or sorry, on disjoint parts of the array, then the resulting sequence is also mutually independent. So general theorem now. Let's write a proof down for this. Let me see if I can write a proof down for this. So the proof for this. So what's the proof? So the proof is so let me add the intuition of the theorem. What is the theorem saying intuitively? The theorem is saying intuitively that random quantities. So the theorem, if I have to say it in words, random quantities are produced from from independent inputs will be independent. Will be independent. That's what this theorem is saying. So we have a proof of this. So let B1, Bn be sets in the ranges of y1 through yn. Okay. So then what I have to show? I have to show that the chance that y1 in B1 all the way up to yn in Bn, this splits up as a product, right? So what is first line? Let's see. So here's an interesting catch. I'll leave it as an open question for you guys to understand. So the first thing is you write down is that this is easy. First thing is that what's y1? Y1 is f of x11 up to xm11. This is in B1. And all the way up to fn of x1n all the way up to xmnn is in Bn. That's what this is, right? Now this is the same as the chance that, so you look at each of these events, so you look at x11 up to xm11 is an f1 inverse of B1, right? All the way up to xn, xmn, and in fn inverse of B. Right? That's just a standard pattern. Now you know that the xi's are independent, so you know that the xi's are independent. So the xi's are independent. Xij are independent, are mutually independent. Right. So this becomes a product of j equal to 1 to n, the probability of each of these guys. So you take xj1, x sub mj1, so mjj, right? X sub, let me say x sub I, let me just do the reverse. Reverse notation a little bit. Let me say I equal to 1 to n. I equal to 1 to n. Let me just go, it doesn't matter. Let me just go j. Let me j equal to 1 to n, xj and mjj is in the event f in fj inverse of b sub j, this product. Now you just go backtrack a little bit, the same as product of j equal to 1 to n, probability that f sub j of xj1 is lagging behind, x sub j of x sub mjj is in bj. And that's the same as the product of j equal to 1 to n, probability that y sub j is in bj. And this I have shown for any possible events bi's, which proves that this will imply that y1, y2, yn are mutually independent. Let me quickly recap the proof. Let me just go double use split view and show you the both sides so it's clear. So let me bring this down a little bit. You can see the proof. Bring this down a little bit. Let me go to the previous page. So this is what I was trying to show, right? So I said that functions are independent if this happens, if you have an array xij and you have functions acting on disjoint parts of the array, then the random variables, resulting random variables, are independent. So this is what's the proof is fairly simple, but there's a small exercise to do in the proof that the green part has to be justified a little bit. But I'll leave it as an exercise for you to think about. And the proof follows that y1, yn are also mutually independent. So the idea is that random quantities produced from independent inputs will always be independent.